Okay. Number one, if you measured the height of 75 males at the school, would you use probabilities or confidence to estimate the true average of all males at the school? Confidence. When you are inferring from the sample to the box, you use confidence intervals. 53% of voters in a state selected a particular political candidate. If you plan to talk to 1,000 of the voters in the state, would you use probabilities or confidence to estimate the percentage of voters you would speak to who voted for the candidate? Probabilities, because we already know what the vote was. We're going to go out there and talk to people and compare our sample to what we already know was true. Now, that's not as useful, right? The probability method is not the point of this class. The whole point of this class is to take a sample and make inferences on the population. So, number 3, you're tossing a fair coin and counting the number of times the coin comes up as heads. Create a box model. There are lots of them. We could create a box where we put an H and a T paper. That's not very useful. There are no numbers. Okay, so I want to create a new box with a 1 and a 0. The 1 represents the head because that's what I'm tracking, and the 0 represents the tail. Now, that box is more useful, but calculating things like the SD and the average takes more time if you have numbered tickets in the box. The box that we want to create looks like what? 0.5 and 0.5. And what we mean by that is 50% ones and 50% zeros. Now, it doesn't really matter that there are only 2 tickets in the box. If I went back to my 1-0 box and I put 1,000 ones and 1,000 zeros, everything is going to end up being exactly the same. So if the number of tickets doesn't matter in the box, then we just get rid of the tickets and we write the percentage of each type. And we usually write winning first and losing second. Okay? And now we've gotten rid of the coin, we've gotten rid of the tickets, we've boiled it down to just percentages. So, what is your expected number of heads in 400 tosses? 200. We expect half of them to be heads. Okay, what is the SD of the box? Can I do the SD shortcut? Yes, which is 1 minus 0 times the square root of 0.5 times 0.5. But we've done this enough times. We know that the answer is just 0.5. Anytime your percentages are close to 50%, so anything like, I don't know, 43% to 50%, then the SD is 0.5. Okay. Which SE should we use in this case? SEN. Why? We're counting how many heads. Okay. So we're going to use the SEN, which is 200 plus or minus 0.5 times the square root of 400, and 0.5 times 20 is, help me out, 10? Okay. So if we do 400 draws from the box, we expect to get 200 heads plus or minus 10. Now, the trouble with the SEN is the more draws we do, the bigger our expected value is. So it's much better to look at percentages and averages instead of numbers. So we're not really going to use the SEN a lot. Okay. All right. So that's the SE10. Interpret the meaning. So 200, we expect to get 200 heads, give or take 10. Now, if everybody plays this game, what percentage of you are going to be inside this window? 68%. Okay. So what is the chance that you will get more than 205 heads in 400 tosses? So I draw the normal curve. My expected value is 200. I want to know 205 to the right. Do I need to use edges? We're kind of in that no man's land between 100 and 600. So if you use edges, then show your work. If you don't use edges, show your work. And they're both going to be correct. They might be off by a couple percentage points, but it's not a super big deal. So to find my z-score, this is 205. So I do 205 minus 200, which is 5, and I divide that by my SE of 10, and I get 0.5, and I'm going to shade norm from 0.5 to 5. What do you get when you do that? 30.8? Okay. So 10 and 11 are basically the same thing, except you're going to have a right edge and a left edge. So do you need me to do one of those? No? Okay. Number 12. We're going to go backwards in number 12. And the hardest thing for number 12 is figuring out where the line is. As soon as you put the line in the right place, it's simple after that. So there is a 65% chance of getting more than a certain number of heads in 400 tosses. So if I have my normal curve, and I want to put a mark where 65% is the place, so that place represents a mark where, I'm really doing well here, where 65% of the graph is bigger than that. So am I going to be right of 200 or left of 200? I want to put a mark that represents 65% larger than that. So I need to put my mark over here so that the area to the right is 65%, which means my z-score is going to be negative. And when you look numbers up in the z-score table, they're always positive, which is why you need to put your mark in the right place. Well, you could create a z-score table that had a right tail on it. So you could do a middle area and a right area and a left area, but we don't want that many posters on the walls. So we've just learned if 65% is right of that mark, then 35% is to the left. And if I cut off that same 35% on the other side, that gives me a central area of 100 minus 35, which is 30%. So I need to look up the z-score associated with a central area of 30%. So area equals 0.3 gives me, what did you guys do, 0.49? Or 0.39? So z is equal to 0.39, but because I'm over here on the left, it's actually negative 0.39. Okay, do I worry about edges? As long as you show your work, I don't really care. Because this is all a guess anyway, right? Nothing we do is exact. So not super concerned. What units are on 0.39? Negative 0.39 what? SE's below average, right? This mark is 0.39 SE's below the average mark. So I need to reintroduce heads. How do I convert SE's into heads? You multiply by the standard error. And so this is 0.39 SE's. Well, I know that there are 10 heads per standard error. And those cancel. And we don't usually write that out, but you might forget. Do I multiply or do I divide? Well, you just set it up according to the units. And we end up with a value that says negative 3.9 what? What does that mean? That's how many heads it is to the left of 200. So I just need to do 200 minus 3.9, and I get 196.1, which means that 65% of the people who play this game 400 times will have 196 heads or more. Now, does 196.1 really make sense here? No, because you're counting heads. You can't have a decimal. So this one can be just rounded down to 196. Now, if you put 196.1, I'm not going to mark it wrong. But 65% of the people who play will get 196 or more. Okay. So 13 is the same. We'll move on to number 14. Did you find any answers that were wrong? No? That's a first. Okay. You plan on tossing a fair coin and recording the percentage of heads. So this box, you have to use, well, you don't have to, but it's much easier to use this one. Okay. What is your expected percentage of heads in 400 tosses? 50%. That's way easier than counting the heads, and it's actually more useful because I could tell you, hey, I played a game and I got 875 heads. Like, great, but how many flips did you do? It makes a lot more sense to say I played this game and I had 50% heads. So the SD of the box is the same. It's 0.5. And which SE should we use in this case? The SEP, because we're tracking percentages. So we're going to get 50% plus or minus 0.5 times, sorry, divided by the square root of 400, which is 20. So 0.5 divided by 20. And you always have to turn the SEP into a percentage. Yes. I end up with 0.025, which turns into 2.5%. When you do the SE average, the calculation is the same, but you don't turn it into a percentage. The SEP will always be between 0 and 1. In fact, it will always be something close to 0. But the SE average, you don't convert it into anything other than the decimal that you just get. So what does this mean? 50% of the people, or sorry, when you play this game, you're expected to get 50% heads plus or minus 2.5%. What is the chance that you will get more than 47% heads in 400 tosses? So we draw our normal curve. We put 50 in the middle, and we want to know 47 or bigger. Right? So that gives me a value of -3 divided by 2.5. So -3 divided by 2.5. And I get -1.2, or not 5, 1.2. And we're going to shade norm from -1.2 to 5. Whatever you get there. 88. Okay. Same thing with 21. Same thing with 22. 23, we're going to go backwards. There is a 25% chance of getting less than blank. So I want to put a mark on here that has 25% of the area to the left. So this is 50, and this over here is 25%, and my goal is to figure out what percentage is right there. Well, if the left is 25, then I need to create 25 on the right, which means that we have a central area of 50%. Now, I realized later that this is a little bit confusing because the expected value is 50% and the central area is 50%. Those are two different types of numbers. This is 50% of your draws will be heads. This is 50% of the people who make the draws. So the central line of 50 represents the percentage of heads. The central area of 50 represents 50% of the people who play the game will land in that space. So we go to the table, we look up 0.5, which is 0.67. So my z-score is negative 0.67. That's in SEs. We want to convert that into a percentage, so we multiply it by our standard error of 2.5. So negative 0.67 times 2.5. And that tells me what? I am 1.675 percentage points left of 50%. So I just add 50 to that, and I get 48.325. So 25% of the people who flip a coin 400 times will end up with 48% heads or less, fewer. Okay? And then we basically do the same thing with number 24. 25, you'll be playing a game where you roll a six-sided dice 225 times. Your score for the game will be the sum of your rolls. What is the box going to look like? 1, 2, 3, 4, 5, 6. Can I change that? Well, I could put 2 of everything, or 10 of everything, or 100 of everything, but I cannot convert this to a 1-0 box because I'm adding up the terms. Okay, so the average of this box, the average of the box is 3.5, and what is the SD of the box? 1.7. Okay, so how many points do you expect to earn in 225 rolls? Well, each roll is basically 3.5 points. So 3.5 times 225 gives me 787.5. So my expected value is 787.5 plus or minus something. Which SE am I going to use? SEN. So you use the SEN when you are counting or doing a sum. Okay. So we need to multiply the SD by the square root of 225, which is 15. So 1.7 times 15. And we get 25.5. Now, I guess technically we got to get rid of those 0.5s. But for our calculations in the normal curve, I'm going to leave them because they'll probably be a little bit more accurate. Okay, so interpret the meaning of the SE. In 225 draws, you're expected to earn or to have a sum of 787.5, give or take 25.5. Okay, what is the chance you will score more than 750 points? Well, I need a normal curve with an average at 787.5. And I want to know from 750 to the right. So 750 minus 787.5. And I get negative 37.5. Divide that by my SE of 25.5. And I get a z-score of negative 1.47. And I shade norm from negative 1.47 to 5. Is everybody okay with that? Z-score is negative 1.47. Okay, 32 and 33 are similar. Let's do you want to do 34 or 35? Everything I've done so far has been to the right. Oh, that's not true. Never mind. Let's do 35. So 35 says, we want to mark an area where 10% is to the right. If I mark a similar area with 10% on the left, that gives me a central area of 80. I look up 80 on my table, and it's 1.28. So this z-score is 1.28. That is in terms of standard errors. I am 1.28 standard errors larger than the average. We need to convert that back into points. So we multiply it by 25.5. and we get 32.64. What does that number mean? That's how far above the average I am. So I add the average of 787.5, and I get a value of 820.4. Now, 10% of the people who play this game will end up with a sum of 820 or more. Okay? All right. Are we going to finish? We might make it. All right, you will be playing a game where you roll a four-sided dice 100 times. Your score for the game will be the average of the rolls. So a four-sided dice has the numbers 1, 2, 3, or 4. Can I change this box? No. I can't, because I need the average. So the average of the box is, so X bar is 2.5, and my SD, I can't use the shortcut. I can only use the shortcut when there are two numbers in there, so I have to plug them into my calculator, do a one variable stat. What do you get for the SD? 1.118. Okay, and we're going to play this, we're going to roll the dice 100 times. So my expected score is 2.5 plus or minus this. Which SE do we use? SE average. So I'm going to divide this by the square root of 100, which is 10, and I get 0.111118. But notice I did not turn that into a percentage. The SE average is just the number you get when you do the calculation. The formula is the same, but with the SEP, you have to convert it to a percentage. Okay. What is the chance that you will score more than 2.5 points? That one's easy. 50%. And then what's the chance you'll score less than 2.9? Do you need to see that? So you're going to do 2.9 minus 2.5, which is 0.4. Then you do 0.4 divided by 0.1118. And then you shade norm from -5 to whatever that value is. And what did it end up being? 90, 99%, because you're like 3 SDs away, right? So once you're 3 SDs away, that's pretty much the whole graph. Okay, 46. There's a 33% chance of scoring more than what? So I put 33% on the right, and then I put 33% on the left, which creates 34% in the center. Go to my table. 0.34 is exactly 0.44. So my z-score is 0.44. I need to times that by my SE of 0.1118. So 0.44 times 0.1118. And then I need to add that back to my 2.5. And I get 2.55. Well, I got 4.9, so I just rounded it to 5. So you're good. Just show your work. I've never been super picky about decimals. As long as you show your work, we're good. Okay. 196. We're going to make it. Or sorry, that's not number 196. Number 48. 196 women in Utah are surveyed for height. The average height of the sample is 62 inches with a standard deviation of 4. Okay. Now, this is statistics. Up until now, we've been working with a box that we knew what was in it. Now we're going to take a sample and use that information to estimate what we think is in the box. So we sample 196, which is nice. The square root of 196 is 14. Wonder if I did that on purpose. And we end up with an average of 62 and an SD of 4. So my expected value, which SE am I going to use? SE average. And so we expect the true average to be 62 plus or minus whatever 4 divided by the square root of 96 is. So 4 divided by 14 is 0.2857. That's the SE. And then there's the interpretation right there. So that's pretty good. We think that the true average is 62 inches, give or take a quarter of an inch. Maybe a little bit more than a quarter of an inch. So let's create a 95% confidence interval. How do I do that? I just times this by 2. And I get 62 plus or minus whatever that answer is right there, times 2. 0.5714. Now, am I 95? Is there a 95% chance that I'm correct? No, chance is a probability. But I am 95% confident that the true average is somewhere in that window. How would you create an 82% confidence? You go to your z-score table and you look up 0.82, which is 1.34. So instead of multiplying by 2, I multiply by 1.34. And it's really that easy. So 0.2857 times 1.34. That's not going to work. So 0.2857 times 1. So this just changes to 0.38. Okay. 53. 250 women people. I'm not going to fix that. I like it. 250 women people in Emory County are surveyed regarding whether they prefer wearing boots or shoes. So let me try that again. 250 women people in Emory County are surveyed regarding whether they prefer wearing boots or shoes to work. 45 people, women people, said they prefer wearing boots. So let's convert this into a percentage. 45 divided by 250. And my box is going to be 0.18 and 0.82. Okay, and we're going to use the SEP. Why? Because we're using percentages. So I expect 18% plus or minus whatever the SE is. So the SD is the square root of 0.18 times 0.82, and then I'm going to divide that by the square root of 250. So the square root of 0.18 times 0.82, hit enter, and then divide that by the square root of 250. And now I need to convert it into a percentage. So 2.4%. Okay. And then create a 95% confidence interval. That's easy. I just doubled the 2.4. How do I create a 98% confidence? I go to my z-score table and I find 0.98, which is 2.32. So I multiply this by 2.32, and then I am 98% confident. Done.